what we did here, differentiation of complex functions, right? I have said we have spent 3 classes on this already. We first tried to understand what does convergence in the complex plane mean, okay? And if I have to say all of that in one line, then it is basically you have a sequence z1, z2, and so on. It converges if the sequence becomes close to, if this sequence converges to z, if the sequence becomes close to it, means that if you draw any epsilon ball, then everything of the sequence beyond a certain point is inside that ball. This is analogous to, as you know, of convergence in the ordinary sequence sense. Okay, but this reduces to the real part converging to the real part of z and the imaginary part converging to the imaginary part of z. Because of the distance formula, you can sort of guess that, right? So this is what we kind of this is what we started with, right? Yeah, and after that, let me quickly give the definition of what a function being differentiable mean. Okay, so if f is a function which is from c to c, what does it mean for it to be differentiable? I mean, that we must understand, right? So it means that limit h going to 0, f of a plus h minus f of a divided by h. This limit exists. And remember, uh, f, so f is differentiable at a. Okay, if this happens. Okay, now what does it mean? It means that the h tends to 0, which means that you have to try out for all values of h in a neighborhood of the origin. Is that right? You have to try out all values of h in a neighborhood of the origin and see if this complex number tends or goes close to some complex number, some fixed complex number, and that will be called the derivative. All right. Let's quickly take an example. I think better because, yeah, quickly take an example. Let's take the function fz equal to z bar. Okay, and fix a point z naught. Fix a point z naught. Let's try to investigate if this is differentiable at point z naught. Z naught is just an arbitrary point. You can take it to be a number also, meaning that just take it to be 2 plus I or something like that. So how can we understand whether this is differentiable or not? Let's see. We take z plus h, f of z plus h minus f of z by h. Limit tends to 0. Okay, just writing the definition. Now what does this turn out to be? If you write the definition, just cutting it short, it will be, so I mean we have done this example, but I'm just doing this again. We'll see. We get this, right? Conjugate of h divided by h, right? Now I want someone to tell me if this is differentiable or not, or what can they say? Means does this limit exist or not? Yeah. So Aniket, you are a little late. I don't mind it, but just that you have missed something. But anyways, I just interrupt me if you don't understand something. Yeah. So I want someone to, especially those who have seen this, to say whether this limit will exist or not. That way, all of us can understand what does this mean, because h is a complex number. H is a number that is values around the origin. So h is tending to 0. Okay, in any way, it can tend to 0 in any way. So we want to understand if this goes to some number. Okay, so if the limit, anybody wants to say, those who have done this? Mhm. Yes. So can you give an explanation for in this particular case in elementary terms? Um, let's see. Yeah. Hmm. H can go close to 0. H bar will also go close to 0, but the ratio has a problem. Okay. See this limit. So let me, this limit exists. Why? Let's do it. As this is very, in the sense that it's trivial, but not a loss to do it. Something like that. Yeah, right. H1 minus I H2. Now, from the definition that we have done, what does it mean? It means that you can take the limit of the real part and the imaginary part separately, isn't it? And you will see that obviously both of them are 0, right? Limit h tend to 0, h1. H is h1 plus I h2, but when you're taking the limit of h1, then the I h2 part doesn't matter, right? And especially when you are taking this one, then here h1 doesn't matter, and obviously both of them obviously go to 0. There is no problem. So there is no problem in h bar, but there is a problem in h bar by h. It is very essential to understand that, because we will prove, when we prove the Cauchy-Riemann equation, which is really the milestone in complex analysis. This will be, we'll see something related to z bars being very, very crucial. So you see, this limit exists. Let me show it in an alternative way. I think it is good to say it in different ways. I mean, let's see it in an alternative way. No, this will not exist, right? But let me show you why this exists in a slightly different way. Okay, this may seem like a bit of a JE type, in the sense that just using properties. Yeah, but let me say it in a different way. Okay, so if you use a very definition, right, then what is it? The definition says that given an epsilon, you want this minus the limit to be less than epsilon for all h in a certain delta, right? Given an epsilon, if the limit of this is L, which we have guessed to be 0, so it is 0. Given an epsilon, given a degree of closeness around the limit, right, you want this to happen, right? You want this to happen. You want h bar to be close to the limit by epsilon amount for all h that is in the delta ball, or in the delta neighborhood in the real case, but in the delta ball. So you want this, but this is trivial, because I mean mod of h bar is equal to mod of h. So you can just take your delta to be epsilon. That's right. It's very simple that this exists. But h bar by h does not exist. Now I want someone to maybe explain, if they can, why it doesn't exist. This is very crucial, because it says that z bar, such a nice function, right? Z bar is such a nice function, and it's not differentiable. If you think about it, it is like this. Z bar is like this. I want the new people to also just, means those who have come to this class for the first time, just see that why I am calling z bar like this. Okay. This function limit, it is not differentiable. It's very strange. Okay. So why does this limit not exist? Let's see. I mean, it is really because you can, so those who, I mean, I'm sure you people must have seen the e to the power I. Yeah. Okay. Mm-hmm. Mm-hmm. For h less than delta, for all h less than delta, we want this to happen. This should imply this. But the epsilon is given first, okay? That is important, because the degree of closeness must be given first. Right? Yeah. So this h bar, this h is in the delta ball. Yeah. You guys can also think of it in terms of e to the power I theta, right? If h is r e to the power I theta, right, okay, basically this is mod 1, right? So this will be e to the power minus I 2 theta. That's what this function is, right? And theta is just varying. Now it is very clear, right? If theta varies, then how will this tend to something, regardless of what the h is? Do you guys see the point, right? This, I mean, we will do it by this epsilon delta method also, which is okay. But you see, by this it is very clear. If this quantity is e to the power minus I2 theta. I mean, the h can go to 0, but the theta will still change, right? No matter how small the delta you take, the theta can still go around 360 degrees, and this will take all sorts of values. This will take all values with mod 1, in fact, no matter how small you put your delta to be, no matter how small you put your h to be. So there is no hope of existence. Okay, that is one way to see it. But this is not the simplest way. The simplest way, I mean, the epsilon delta way will not be simple, I think. But since we have done this, maybe you guys can think about the epsilon delta way later on. Meanwhile, I'll just show you the standard, the textbook way. How it is done in the textbooks usually is, so you'd say this, okay, then we say that you do tend to etch in two different ways. See, whenever you want to show the limit of something doesn't exist, right? Sequences are usually the best way, a good way, because you take different sequences tending to zero and you check if you get different limits or not. Isn't it? If you can find two sequences in which you get different limits, then obviously the limit does not exist. So you take h to be real first, meaning that you tend along the real axis towards zero. Yeah, but I think this I just thought of this now because the theta thing, 2 theta, that is the interesting way to see. But this is very easy to see like this, right? And this will be fundamental for us when we derive the Cauchy-Riemann equation, this technique. So when you tend along the reals, it will be 1. But when you let h be imaginary, then h becomes IH, something like that. And this becomes, you can check, this will be -1. Right? So this is another technique for all of us to take home, is that you just try different sequences. And yeah, the next case we tend along imaginary. So let h be imaginary. So h will be I times h1, and you can put that and see that it will be -1. And as I said, it's not just 1 and -1. You can make it any value, right? You can make it any value with mod 1. You can make it any complex number with modulus 1. Do you guys see the thing, right? Because it's e to the power minus 2, e to the power minus I2, right? It's so obvious. You can make it anything. So this is the thing, it's more, it's so this complex analysis is just term analysis, but really your aptitude of complex numbers will be very useful here also. Okay, just especially geometrically, what you can see. So with that in mind, let me not go into more differentiation just at the moment, but do something which is complex logarithms just through a problem, because complex logarithms are essential again for us. We'll soon see, but here I'll just introduce you to a problem and we'll see what all we can do. Okay? So the problem is like this, okay? This can be just a problem, okay? So find all x belonging to complex numbers such that, so I'm intentionally not defining anything because I don't want to go into theory of logarithms, but just want to understand it through a problem, okay? Find all x belonging to C such that log x, okay? Now, you can make your own definitions now, but we'll do a formal definition later on if needed. Log x has the form b times alpha, where alpha is a logarithm. This will maybe force you to think about logarithms in a very fundamental way, because usually for logarithms we just apply all the identity. Let's see, alpha is a logarithm of a in complex, b is also in complex, b is in C also. Yeah. So of course, there will be multiple x. Let's just see what you people understand from this question, because I have not defined logarithms, and maybe not all of you know complex logarithms. But anyways, let's see. Right, that will be a better definition. Yes. So yeah. Okay. Then let's see. Let's go on then. Right. So Raghav is saying that log x, what does it? So, and what does log x mean in the real world, right? In the real world, it means that what power do I need to raise e to get x, right? What power should I raise e to get x? And that is basically this identity as well. This is a definition of log, right? So here also, log x would be, this is not a number now anymore. Okay, this is a set. Okay, this is a set of stuff. Okay, maybe I can just call it a t, such that e to the power t is equal to x. Now let us think. Now we have a better way to think. So I'm intentionally not formally introducing because really there's no need. People are smart enough to understand like this only. So some theory has to be done, like maybe for this class also, before we can see some benefits of this, which I mentioned in the beginning of the class. Separate what? Okay. The log of this you're saying, yeah, that is partially correct. It's log r plus plus what? Plus I theta. But what else can we say? It is so. This is one of the values. As I said, it's not a number. It's a set. This is one of the values. So I'll just say you people can figure it out. Plus 2 pi, right? Because all those also will satisfy the same. Exactly, right. 2 n pi, 2 n pi. Right. So how do we use that to solve this problem? And there was some other piece of information which I'm missing. The problem is looking too many alphabets. So 1 second. Yeah, and there's a there are conditions that is a is 1 and b is 1 by 3 plus I. Then it becomes a MCQ or exam question. 1 by 3 plus I. Right. So see, log x, as you're saying, this set log x, this set must be equal to, as I've said, has the form b alpha, right? B is a complex number. I'll write the value, but b is a complex number. And that's really about the problem. It's more about understanding this. The problem otherwise is not a problem. It's just a exercise. Log a. So I'm just saying that these two sets are equal. And you want to find out the set log x. I'm just translating translating the question. The question was given in a more complicated way. I've translated it a little bit, but just to so that we can parse it with high school terminology. And then we have this, right? This equation. Now you can try to solve this. So a was 1, right? So you can put it. I mean, I'm sorry. This is 1 by 3 plus I. So this is nothing. Just putting the values. Now what can we say about x? So we can say that x will be equal to e to the power this, right? What? This thing? No, but if you okay, so let's do it steadily. You can write this as log e 1 to the power 1 by I, right? But what will this be? I mean, what is log 1? Okay, sorry, that's 1 second. Yeah, no, log 1 is, that's one of the values. That's one of the values, but that's not, those are not all the values, right? What are the other values of log 1? Yes, right. 2 and pi, right? So this set is like 1 by 3 plus I. You don't even need to lift it. Yeah. You can just say like this. It's 2 and pi, right? It's like this. And then no, so we must say I2 and pi, right? I2 and pi, yeah. Yeah, I2 and pi. And then this is what is equal to this. And then for x, you can just raise it to the power e. So this is your answer. And you can simplify it a bit more, but it will be something like this thing. And you can simplify it a bit more after canceling. So you see, we get a set of values. This is your x. Okay. So, yeah. Maybe try doing it in a different way if you want to. Think about it. Cool question. So we'll need these kind of ways to manipulate these things fast. Otherwise, because we won't always get intuition for complex functions, and especially we won't always have the time to think about it and so on. So yeah. All right. So that being out of the way, let's come to the real matter. What was our goal? So as we saw for the z bar question, right? It's not so easy to decide if a complex function is differentiable, right? And we cannot always use the because look, if you're in reals, then the limit taking process is slightly easier, but in complex you cannot always use the limit taking process, right? Because the limit is on us on a ball, by approaching on a ball. So we need good criteria, right? We need good necessary means essentially we need sufficient, but necessary and sufficient, if we can get criteria to decide. This is the key for us, and we get much more than this in return, we'll see. But yeah, to decide. But for now, this can be our motivation. When f from c to c is differentiable. Okay, it's differentiable. So for this, we had spent one class on motivating, derivatives of R2 to R2. So today I will not do the motivation, but just the definition. But really, just to make it in very short, one thing was like this, right? Any complex function from C to C can be seen as u of x comma y plus I v of x comma y, right? So this can also be seen, so f can also be seen as a function from R2 to R2. Okay, R2 to R2, pairs of numbers to pairs of numbers in the plane. R2 to R2, where x comma y goes to ux comma y comma vx comma y. But obviously, the natural complex numbers that you can, the natural complex functions that you will think of there, that this is really the sort of a philosophical point, meta point that will make the results coming up not so surprising. Is that when you take a natural complex function from c to c, like xz going to z square, you will see that this u and v will have a lot to do with each other. Whereas if you just define a function from R2 to R2, the u and the v will usually you can just define them to be, you can just append two functions, right? From R, just like we had, right? You can take a function from R2 to R to be going to x, and you can take another function like this, and you can append them. This is not a natural function. This is not a natural complex function, right? This is what z conjugate is, and it's not differentiable. So my point being is that when you take a complex function which is naturally arising, then usually the u and the v will be related to each other, and we want to really give out the equations with which they are related, the exact manner in which they are related, we want to say. And then that will be like a necessary condition, right? Because we'll assume differentiability and get those equations. But then we will show the reverse also by adding a few more conditions, and then we will have the theory to get started with all the power series and all the applications. Okay, so u and v will usually be related in good complex functions. Okay, and z bar we know is a bad complex function for differentiation. Okay, so we said more about this, but I will not say more about this today. Not repeat. Yeah. Right. So where are we then? We see that it then becomes important for us to understand what it means for a function from a function from R2 to R2 to be differentiable. Okay. The way we have set up the differentiation theory in the parallel class on real differentiation also, we have a lot of sense about this already. But again, to cut it short, if you want to describe what is the derivative of a function from R2 to R2, right? This job will break this job down to two things. One will be differentiation of this function, and the other will be differentiation of this function. Now the question is, well, how are you going to define the derivative? Okay, and how will you answer that question? The answer is, what do you want to measure, right? So usually, and this we had discussed at length the last time, is when you take this function, right? Some function x plus y, x comma y going to x square plus y square, something like that. This will be a curve, right? Some curve like this. What you want the derivative at a point to do? You want the derivative at a point to maybe capture the slope of the tangent plane, right? And then we had discussed this, that the slope of this tangent plane is determined by two things. So want to calculate, because this is in strict analogy with what you do in the real differentiation, right? Want to calculate the slope of tangent plane at some point, x naught comma y naught. And this, obviously, you people guys know that this will be determined by two things. This needs three pieces of information, but already we know a point through which the plane is passing. So we need two more pieces of information. And we had shown this the last time by, taking a vertical plane and a horizontal plane and so on, that this can be reduced to taking the partial derivative of this. Now, we don't need to know anything about partial derivatives here. I'll just say what this means. Okay. We just need to know, I'm sorry, the v doesn't even come here. We just need to know these two things. And what does it mean? It means nothing. This just means that just treat it as a function in x and take the derivative, meaning that just move along the y coordinate, or move parallel to the x coordinate, the x axis. And this just means just treat it as a function constant in y and just take the derivative. So constant in x and take the derivative with respect to y. That's what the second one means. And these two are the only pieces of information that we need to know to find the tangent plane. So we will define our derivative in a way that captures this. Okay. Right. So then I will quickly give an unmotivated definition, because the motivation would take some time the last time. I've already given some motivation here. And this is how it will be. So let's write the definition of derivative. What is it? We want to see the change. Okay. So now we are writing the definition of derivative in the for a function from R2 to R. Okay. What does it mean? So it will not be a number. As you saw, we need two quantities. We need two numbers. We need two pieces of information, right? We'll try to encode that in our definition. So really, you change the h, subtract it with the function. So basically, you want a linear approximation of the function. You can say it like that. But I'll do one thing. I will not call this x. I will call this x naught. Because see, I want to give out the impression that x is fixed. It's very important to fix the x here, because already there will be a lot of complex things going on. Okay, complex here means complicated, a little bit complicated, not really complicated. Still just get used to it. This difference. Okay. Now, usually, if this was the real differentiation case, then what would you do, right? You would just divide this by h1 comma h2, and you would say take the limit of this. But does it make any sense in in two variable? No. What does it mean to divide by a two variable vector? Doesn't make any sense, right? But then you can, again, I'm not going to repeat all that, but you people will just think about it a little bit. You can see that this also reduces to the following. You can bring the derivative on the left side. Just think about real derivatives. Just think for a moment that u is a real function from R to R. And what does it become? This will become whatever this d is our derivative. Okay, I don't know what that is. Okay, times h1 comma h2. Right? I don't know what d is, a number vector matrix. We don't know for the time, but something like this, right? This h comes here, right? So you have f of x. Just compare it in your mind here like this. Minus f dashed x at h divided by h. This should go to 0, right? So we bring it, and now we cannot divide, but we know that if we could divide, then we would want this to be 0, this limit to be 0. But we just need to make sense of this division. Okay. So remember, we are not doing C to C function right now. We are doing R2 to R2 because that's the first step towards understanding C to C. Because really, deciding whether a real function is R2 to R function is differentiable is easy. It's relatively easier, and then with some more conditions that will help you to decide differentiability for function from C to C as well. So that's fine. All right. How to make sense of this? Well, we'll say, okay, take the mod first. Take the mod. Now, what does mod here mean? It just means the Pythagorean distance of this from the origin. Just it means that distance. Though there are some theories that say that any distance works, but yeah. So this mod just means h1 square plus h2 square. But usually we'll not have to do any calculations as such too much, at least in this class. This is theoretical. We want to understand the behavior of things. So what should I take? What should I call? We should say that the limit. See, I have to take the mod first. I have to take the mod first. I cannot, otherwise I cannot take the ratio. Okay. This is slightly unmotivated maybe, but we had seen complex derivative definition, that how complex multiplication is like a matrix multiplication, rotation, and we had seen all that. But here we are just having to cut it a little short. Okay. So this limit as h1 comma h2, basically we'll soon just write it as h goes to 0. Now this limit makes complete sense, right? Now I could have not defined it by putting this thing on that side. I could not have done that. I mean, see, people may ask that why didn't you do something like this? Just h mod maybe. Why didn't you do something? There's no need of this now. Why don't you do something like this? Yeah. See, the point is that because you would have to take the mod first, right? So why didn't I first take the mod less like usually and then take the limit? Say the limit of the mod on the both sides are equal. Why didn't I take this as a definition? This is a bad definition because see, two vectors. These are vectors. These are not numbers, right? I mean, this thing is a vector. This thing has to be a vector because this thing is a vector. You see, I mean, okay, no, sorry. I mean, it's 1 second. Okay, that this, well, yeah, this is really a problematic thing. This, yeah, this doesn't even actually make sense. That's the point. This doesn't even make sense because what? Okay, if you just take the definition like this, right? If you just take the definition like this, you take the mod and you take the limit, right? Then the point is that you don't even know what D is, right? You don't have any conditions on D. But if you do this, then what you're doing in short, if I have to say simply, is that you're taking mod of two numbers and then you're comparing the limit, right? But we know that several different things can have the same mod. And so this is like a lot of loss of information. Many things can have the same modulus, right? I mean, you can think about a lot of numbers on a circle will have the same mod. Cos theta plus I sin theta, any theta will have the same mod. So limit of the mod does not say much about the equality of the underlying quantities. So that's why this is not a good definition. But there is one thing whose mod and the number is the same, and that is the number 0. And that's why we first take it 0. So like this limit of the mod going to 0 does imply to a large extent that this thing is also certainly going to 0. Like, it cannot go to 0 some other, is because 0 there's only one thing that whose mod is 0 and the number is also a unique number corresponding to the mod. Okay, that's why this definition makes sense. Okay, so that's really one way to understand it a little bit. But this is again just symbolic motivation. I have not given any not arrived at this too much gradually. Right. Now let us come to what is this? What is the D, right? Any guesses as to what the D should be? Just you can just say it based on what these other. Just you can say it based on what is that called in physics? Dimension analysis. Use that to say what D should be. Sorry. Should use? Yeah. I guess someone would have guessed, I think. No, I'm just saying, what should D be? Because I've just said D is a derivative, but then what is it? What should it be? It can't be a number. The point is it cannot be a number. I mean, we have already, because we want to calculate the slope of the tangent plane. But Even if you forget about all that motivation. That's right, but what is it? What is it? Is it a number? Is it a vector? Is it a matrix? What should it be? Given that u is a function from R2 to R. See, this is a number, right? This is a number. Now, if you have to make this a number, this D should be a row vector. Then you can do your dot product. That is the most natural way in which you can make D times H1, H2 a number. And it also goes in parallel with our point of that you want your derivative to capture two numbers. One number will never do it because you want the slope, right? So you want two slope. Actually, when it's plane, you need two more pieces of information after the point at through which it passes is known, right? I mean, if the plane passes through the origin, equation is like this, but this is really just you need two things because you can normalize it with respect to A. You need this and this, right? And we had seen in detail that those numbers are partial derivatives, but anyways. But it's very clear that you need two things, right? So this will be this vector, okay? So the derivative, and this is at the point x naught. Everything is happening at the point x naught, okay? So the definition would be that you need a matrix. Here it's just 2 by 1, so it's just a row vector. You need a matrix, and this is the dot product. Now everything here is a number, right? Now everything here is a number, so all the quantities are same. So there's no dimension analysis. So the definition is this. Now let me repeat the definition again, okay? U from R2 to R is differentiable, is said to be differentiable if, or the definition rather, there exists a row vector A comma B, just like there exists a number f dash x naught. Here, maybe I'll parallel write this also. Just like we say, right, there exists, now we have seen this in the derivative class, that's because the derivative is unique and other things and nonsense, which is not very useful. I mean, it's fine if you don't know it also, doesn't matter. You can still raise your own intuition here, right? This is the definition in the real case. Sometimes it's a very useful definition, right? So we say that there is a number L, that's a 1 by 1 vector. Here we are saying just replacing that by there is a matrix, or there is a 2 by 1 vector here, A comma B, such that this limit is 0. Okay, this basically means that this function is very well approximated by this quantity. So around the point x naught comma y naught, this function is very well approximated by this function. This is what is known as a linear function, because if you change h1 to h1 plus h3, it will also change to h1 and then at h3, evaluating at h1 h2 and h1 and h3 h2, so on. So, but we don't. It's fine. Very good approximation. It goes to 0 faster than the denominator goes to 0, and so on and so on. A lot of interesting things. But yeah, simply for us, it is this. Right. So as I've said, some motivation part I've not said, but I can share it with the others later on if needed. This is a fourth class. So yeah, this thing. Now the question is, well, this is a very good definition, but it's like the problem is like it's like an epsilon delta definition. It's not much usable. It can be used to prove theorems, theoretical theorems, but doesn't give us any criteria, right, as to what is going on. What is this A comma B? How should one find it? How to use it in problems, and yeah, right. And how will it? Right, okay, yeah. Practical applications, yeah. Also, but before that, we must know what this A and B should be. What this A and B should look like. So for that, we specialize as basically like a practical. So you're approaching it, let's say along the x coordinate. Then what? So let's see. Now, because this limit exists, Yes, exactly. Yes, right. I mean, that theoretical definition is not very useful, right? This in the same way. This is, but one has to know this. Otherwise, yeah. This is the thing. But what is the A and the B? So it's very clear what. See, you people already know the A and the B would be the partial derivatives because that is needed, that information. But let's deduce that in fact, right? So look, if the limit exists, it means that it must exist no matter how you approach zero, right? So remember here we are assuming that it's differentiable. So whatever we'll be deriving will be necessary conditions. They may not be sufficient conditions. Okay. So yeah, this is good enough for engineering purposes, but for theoretical purposes may not be good enough. Right. So let, or better to say, um, better to say, yeah, the best to be would be, okay, first let me say like this. So no, wait. First let me say like this, fix h2. Let's say fix h2. Then let me say, let's fix h2 to be 0. This doesn't make it a number, it's still a vector. H1 comma h2 still a, h1 comma 0 is still a vector. But we are fixing h2 equal to 0 and then calculating the limit. Obviously the limit should still be 0, right? This whole limit has to still be 0. It cannot change suddenly, right? Because if the limit exists, it must exist however you calculate it. But what does it mean if I fix h2 to be 0? Let's just patiently, let's write it. So you may think the notation is so clumsy, but the notations will simplify soon. Right now we are just trying to see everything in front of us. We have to write everything. But the magic really happens here in this part, in the matrix. Right, exactly, right. That's AH1. That's correct. That was what I was trying to say. Yes. So now I'll erase it and write it. So you see this matrix thing becomes AH1. Now this is starting to look like a function of one variable to a function of one variable. Like the y naught is just, you can put, you can just erase that in fact, right? It's just a constant. It is AH1. Right. So what is this quantity? Right. I mean, this is just like H1. This is H1, mod H1, right? This also becomes mod H1. To be very, very clear. Now what is that A now? Now we know from the real case, right? If you fix y naught, if you fix y naught, this is a function in one variable. Y naught is not playing any part here. Now, some texts they say that define u x comma y naught as gx, then this will become ultra clear, becomes f of x1 plus h and so on. But I think if everybody is okay, then I will not do that and just it's right here. Now this is just this maybe a little fierce, frightening one, but I think doesn't. I think no. I think people are already facing it in physics, so it's okay. This thing, there are a lot of nuances in this, but right now we are just deriving a necessary condition. It's always easy to derive necessary. That's how maths usually proceeds, right? You derive necessary conditions, and then you see what bunch of necessary conditions are important for you to be able to go back. So that means deriving a sufficient condition, which is really what we want, right? Uh, um, if you want to show when the derivative exists, with necessary conditions you can only show when it doesn't exist, right? But yeah, so anyways, so this just means that you are taking the derivative of u with respect to x. So this is just a notation for just fixing y naught and taking the derivative at the point x equal to x naught. Maybe I can also mention that y equal to y naught, though that is always fixed. You can put y equal to y naught first and then take the derivative. In fact, you can do that, which is actually the tricks which I used in, which we'll not do today. This is more about theoretical discussion.
So this is sorry. Sorry. I mean, what did I do? This is 0, right? This limit is because yeah, this limit is 0. So this is equal to a. Does anybody have problem seeing this? This is a because this is the derivative. This a is the u dashed x. Forget about the y for the time being. Right? If you can find the L here, then this L has to be the derivative. There is no other thing you can place there. One can prove that. It's not hard. The derivative is unique. You can just say that. Everybody's okay with that? A is this, right? So we know the A. In the same way, B is the partial derivative with respect to y. Awesome, right? The A and the B are, if the derivative exists, then this is what A and the B should be. And this is exactly what we needed to find the equation of the tangent plane. Now, that part I've skipped a little bit. You guys, please think about it now. That I said the last. I think last class only we had done that. In the third class of this. And of course, this is at y naught. No. Yeah, this will be at y naught. There you have the x will be fixed. Right. So now we have a very quick way to find the derivative. The derivative will be this, and to find this is very simple. You just take the derivative of the function with respect to x, which is easy, with respect to y, which is easy, and just put them in a matrix like this. Simple. Okay, so now I will remove this. But the hard part, and all this has to be done to understand complex analysis, the Cauchy-Riemann equations. This has to be done. There's no escape, or has to be assumed completely. Meaning that assume the otherwise, because if you assume and you don't know, and if you still assume, then because we'll prove the same thing for Cauchy-Riemann equation, the sufficiency, and if one hasn't seen the sufficiency of this, then they won't just believe it. Because Cauchy-Riemann equation is very important to understand why that happens, why those relations are there. Otherwise, like me, you will keep forgetting it, which I did for 2 years. Even now, I not so good at it, to be honest. This is a way in which I'm learning. So the point is that, look, this is what we had, right? Now, for V also the same situation would happen for V, right? But instead, if you consider U and V, okay, let's not do that. Let's not consider it together. It will become not needed, unnecessarily complicated. Okay. Right. So how can we summarize all this? It's important to summarize things in the end. If U is differentiable, or U said to be differentiable rather, but yeah, if U is differentiable at x naught comma y naught, okay, then this matrix is nothing but there's no comma. Why do I make this mistake? Should be this. But again, this is not sufficient. Maybe this is not sufficient. Okay, there are counter examples again, but not going into that because we have to do complex derivatives. This will already take another one class. Yeah. But then when is this condition sufficient? Okay, when is this condition sufficient for us to conclude that f is differentiable? Okay, so we'll now show that f is different, or u is differentiable, if those two partial derivatives which we have seen, those are just actually real derivatives. This is actually a real derivative. This is nothing, there's nothing multivariable in this. Y is fixed. This real derivative is continuous. The derivative is continuous. The derivative is also a function, right? It's continuous function. And this is also continuous, around x naught and y naught. That's what around x naught comma y naught, both are continuous, which means that the derivative exists in a neighborhood and also it's continuous. So that's a strong condition. In the real class, we had seen that those are not, all those are independent statements. Okay, but before doing that, let me state another way, another criteria for differentiability, which will be unnecessary in our proof. That's why I'm stating it. I'm going to state it. So let's first state it in the real case. For the real case, people have seen, those who are here, but otherwise also you see, maybe you have seen this, is that, look, when f is a function, this ratio you take, right? This is the ratio of the slopes. X is fixed here. This is a function, well, you can say this is a function of h. Fix the h, fix the x. It's a function of h. Okay. Then what do? You just say that, I mean, how do you define this function at 0? You define it to be f dashed x. Right. So if f is differentiable, then there is this function phi h which is continuous, right? If f is differentiable, then this phi h is continuous. This is a very important criteria for all the proof of chain rule and all that relies on these things. So you must know all these different criteria. Otherwise, in problems, this as we did this one. There's another one which is in fact also very useful. None of them are hard to see. I'm not saying some deep thing, but just things that should be available at our disposal in the front. This, and also if this happens, meaning that if phi x is if phi is continuous, then if phi is continuous at 0, then f is differentiable and its derivative is L. Again, if you don't know it, note it down, try to prove it. It's not hard. Okay. So I repeat, and all of us can try to prove this. Okay, those who have not done, even if you have done it earlier and don't remember it now. So if phi is continuous at 0, then f is differentiable. And if f is differentiable, then phi is continuous at 0. Those two are equivalent conditions. Now the same thing, which I'm not going into the proof of, it's straightforward, but just needs a bit of more notations. That's why there's no insight in that. We'll say the following. Because we cannot put h at the bottom, we will say that. So let me state it proper way. If f from R2 to R, like a two-variable polynomial, you can think about. Okay. If f from R2 to R is differentiable, then there exists a continuous just means, continuous is simple, just the distance. Okay. Continuous function phi, continuous at 0, I mean, such that this happens. Right? Well, now once again, what must this phi of h be? Phi of h cannot be a number, right? Phi of h must take input h, which is a vector, a 2D vector, and it must give out a matrix, right? f1h, f2h. See, once again, you cannot avoid this. If you don't give out a matrix, this will not become a number. If you don't give a row vector, I should say. I'm all the time saying matrices because usually we are used to doing this in Rn to Rm in general. So usually that has to be usually a matrix. Okay? But we are breaking it down to the simplest version of multivariable calculus, and so it's a row vector, 2 cross 1. Phi h is not the derivative, okay, but continuous function phi h such that this is true, and limit h tends to 0 phi h is our derivative, which means that it is here the u is replaced by f. It must be the derivative, right? Or rather, those two will become the partial derivatives. And the converse is also true. The converse is needed. If you're going to use this condition for proving something is differentiable, you better have this as a sufficient condition also. So this is converse is also true. Well, what is the moral of the story is that you don't have to observe everything in very detail here. Point is that when you want to show something is differentiable, just take the difference and study it. Take the difference and study it. You'll be shocked how powerful this technique is. Okay, you can prove the chain rule. Maybe I'll say it once in the
real derivative class again. You can prove chain rule, all sorts of complicated statements by just considering difference and doing some sort of a big O small o approximation techniques. The power of that is immense. Okay, because it really see, because we think derivatives are like some very novel thing in the sense that yes, it's a strange kind of ratio. It's a very profound limit and all that. But no, in the end, the derivative is just an approximation. Right? It's a linear approximation of the function, right? So you can use approximation techniques. Just take the difference and show that the difference is sort of a linear thing. The difference is sort of a linear function. This is a linear function. Phi h is a matrix, a linear function. If you replace h by h1 plus h2, then this will just split phi h1 plus phi h2. So that's all. That's all it is, right? It's not something to be feared like that. So that's why take the difference, study it. That's what I'm going to do right now, okay, to show the sufficient. So just take the difference first. And this is the exact template that will be used in the Cauchy-Riemann equation as well. But here we need it because then we can derive a condition for real differentiability, which we will use in complex differentiability also. Okay. So assume that this and this are continuous. Okay, we will, actually, see, you don't even have to put those assumptions in the beginning. You first start taking the difference. Along the way, you will realize what all you need to assume and so on. You will see it for yourself. That is better, right, rather than putting these conditions in the professor kind of way or the lemmas. So because they assume they want you to do it, you see all that, work out the real sequence of the proof yourself. Okay, but never mind, that's fine. So we take this. So we study this difference, right? That's what we are talking about. Just the difference. No limits, nothing in the beginning, just the difference. So, right, the goal, the goal is U is differentiable, meaning that such a thing exists, such a and B exist. And of course, then that A and B will be partial derivatives, but first we have to show A and B exist. U is differentiable at x naught comma y naught. Okay, but we cannot do it like this. No, I'm not saying we cannot. One can, but this is one of the proofs, one of the ways which I should say I remember. The goal is to show that it's differentiable. Consider the difference. All these techniques are useful throughout. Here we'll just consider the difference. Right. Now what do we do with this difference? What can we do? Well, we know about partial derivatives, right? We want to show in the end that partial derivatives will feature in. And it really depends on one variables. The partial derivatives depend on one variables. So this is like the change has been made from x naught comma y naught, the input space, to x naught plus h1 y naught plus h2. Okay, but we'll make this change in two steps, right? So that this problem becomes two problems in real differentiation. That's really the only way to do things, right? You do it from the easier case, break it down into several easier cases. So what is this? Yeah, it's like this. So here you are basically just going to take the partial derivative with respect to h, with respect to first variable. I'll say the details. And this one is like taking partial derivative with respect to the second variable where this is fixed. Only the y naught is changed. Okay, this will be generalized same way if you're doing from Rn to R function, but probably we'll be confused now if we do it. Okay, but no, the point is that same thing will be done. Okay, so what does it mean? It means that this difference, I will change this difference to, let me write it in the next line only. It will be better. Yeah. So as I've said, we will take the difference in two steps. So this is the second step. This part is the second step. And yeah, so we want to see, because what is our condition? Our condition is like this, is based on these things. We want to show there's a matrix of this kind and so on. Yeah. Then what is this? In this one, the y is fixed. Just adding, subtracting this. Same thing, nothing has changed. Moving this. Right. Now, as I've been stressing, this is just a function in one variable. Think of it as a function in one variable. Okay? If you do that, then how do you approximate this distance or this difference? How do you approximate this difference? You see a quantity like this, and typically you'll also have a h in the denominator. How do you approximate this distance? So we use the mean value theorem. This is a function in one, treat it as a function in one variable. If you are not comfortable, you can, or rather, I was getting uncomfortable. You can take g. You can take. It's just the way to say. You can take it like this: gh1. You can take like this, right? Then you can see that this is g of 0. This thing is g of 0 and the difference. Then you apply the mean value theorem. G dashed something, right? This will become g dash something, which means it is u dashed x naught plus not h1, some other h, right? H some h3. Y naught is just there hanging around, it's just fixed, times h1. That's the difference. Is this point okay with everyone? See, why am I able to do this? Because u is the u as a function in only x is differentiable not just at a point x naught but in a neighborhood, because we have this condition, and even if you don't have that condition, you want this, and so you will say, okay, let me put that condition. Okay, so this is what we are putting, is a condition which is allowing us to do this and will allow us to prove that it's differentiable, which means that this is a sufficient condition. But this is not the best sufficient condition. There are sufficient conditions which are closer to necessary than this is, but those are not that common, not that useful maybe. Okay, this is the cleanest condition, that is, derivatives is continuous. So we write it like this. Now you can do the same thing for this. Here it is okay, so I should just maintain something here, is that I should not call it like this. Okay, but this is, as you can understand, this is just Lagrange mean value theorem. If someone doesn't see it, please say. This can also write it as g dashed this times h. Same thing. Yeah. Now for this one also you can do the same thing, but here x naught is not x naught, it is x naught plus h, and that will become y naught plus h3, and h2 is the difference, derivative with respect to y. Okay, you guys are fine with this, right? Okay, so what do we have? We have seen that the difference of the function, something interesting. So remove some, let's take a second to absorb. We can meanwhile, just remove and clean up a few things for the final. So the last step, yes, sure. Yeah, you mean this difference one? Okay, this difference one, right? Yes, okay, sure. Right, so then let's remove this. Let's remove this and say it. Okay, this time let me say it from this one. Okay, see, so let's see, consider this as a function in the second variable. Okay, so let's call this gy. Okay. If you call that gy, you fix the first variable. You're not changing it. Then what does this expression become? This one becomes g of y naught plus h2, and the other one becomes g of y naught. Yeah, that's fine. This one becomes this. Now we apply the Lagrange mean value theorem. This becomes g dashed y naught plus h4 times h2, right? Why am I saying this? Because y naught plus h4, of course, this has to be a condition, is less than y naught plus h4 is less than h2, basically. This condition, right? I'm writing it down just to remember the y naught. Okay, not very essential, maybe. Okay, and the h2, right? And now just break it down to the definition. Let me just keep it here only. Yeah, it's good to see this like this because this sort of parameterization sometimes is useful, sometimes essential. One parameter groups and so essential. This thing now, if you again unbox the thing, what have you done? You have just taken the derivative of u with respect to y. Where have you taken it? You have taken it at the point y plus y naught plus h4, right? And then you have multiplied this with h2. So everything is real. Yeah, if these real derivatives. Okay. Yeah, is this step fine? Right. Okay. Okay. So that's all. So the first, this one is also like that. This one is with respect to x at x naught plus h3. Okay. But we don't do this usually. We just write it and we understand it that yeah we because it's like a function only. It is a function. It's a proper function from R to R. In fact, you're taking this derivative at y naught plus h4 comma x naught plus h1, but that's fine. And here you're taking it at x naught plus h1. This times this was there was a h1. This is h1. This is not h1. This is h3. This is h3. Okay, sorry. This right. So if you again, it's just a lot of details. Though if you look back, it's just simple. Means even that if the steps become comfortable, then there's not really nothing ingenious going on here. Okay, I mean in the sense that this all this just take time to develop. We are just absorbing it. I've just read it, so yeah, it's like this. Now you see, this is exactly what we needed. This h1 h2 is our vector, and this is our phi. I mean, this is just a function of h4, in fact, right? It is just a function in h4 phi u x naught plus h3. Right? As I was saying that this difference, if you forget about, so this is fine. I'm just removing all this. This is what we have proved. Now you see, it's quite believable that we have arrived. Yeah, this looks like we are done, isn't it? This is the function phi. As we were saying, right? There has to be a function phi. Phi has to be a function of h, right? Phi. One second. There is a slight sleight of hand going on. Phi is a function of h is correct, but there is h4 and h3 here, right? That is the how do I amend that? I do not know immediately. H4 we are getting this. No, it's h3 h4. So this is a phi. As I was saying, right? Phi takes in a vector and gives out a matrix. It has to make it a real. It's continuous. Now why is it continuous? Because this is a continuous. The derivatives are continuous, and they have this. And so this is basically, as I was saying, another formulation of f being different, u being differentiable. Yeah. The only issue is that this should have been this cannot be h1 h2. This has to be h3 h4 in the way we have done. But then how is that a function of h1 h2? Means phi is not a function of h. It's it is a function of h, but then it is not a function of h. So that's where I am slightly confused. So it's not a problem because it's all continuous, so the values are the same. But just give me a minute. One second. Yeah, because we have applied the mean value theorem, you will get a value in between. You will not get. So when you take the difference and you take the derivative will be at some value which might be in between, and that you yeah, that is usually shaken off, because it's continuous. So I mean, this will be almost same as this. That's just other than that we are done, right? Other than that we are very much done. I mean, if you want to think of it, you can just take the difference, though it's not mathematically speaking correct, but you take the difference, it's kind of going to zero, right? Because phi h. Oh, what happened? Array. Yeah, this is kind of mm, right. Yeah, never mind. So this, according to the definition, this is almost fine. There is just a slight here. I don't know how to resolve that immediately, but yeah, kind of says that u is differentiable. So the conclusion is that you take your partial derivatives and see if they are continuous. If your partial derivatives are continuous, then your function is differentiable in the in the right sense, in the sense you have defined there is an a and b such that this will work. Okay, so all of the techniques which we have picked in between. Okay, now next time we will apply this to complex numbers, and we'll see that in the complex case these matrix will be special, the a and b will be related, and of course there's a c and d also waiting, and all those four quantities will be related. We'll see the relation very nicely, though we have already seen it in some sense before. We see the relation, and then that will be the conclusion. But then we can also go reverse, and there's another technique which we'll use to go reverse and show that that's if and only if. Yeah, then we can slowly move into polynomials and actually applying it, and a lot of interesting applications for Olympiad questions, and also more proving more higher math results and things like that, right? So I think that is it for now. Friday I think we'll have a class on the real derivatives that's more relevant and so on. Anyways, that's it. Thank you. Any questions?